come back. Now, depending upon the media, the materials, we might get mostly reflection, we might get mostly transmission. Generally, we would say when the two materials are very similar to each other, we get mostly transmission, and when they're very different from one another, we get mostly reflection. In the demonstration we just did, the slinky was attached at one end to Dammy, so the wave was going from slinky to person, and we found that most of the wave in that case was reflected. But if we were going from one slinky to another slinky that was just pretty similar to the first slinky, then most of the wave would have kept going. So we always get some of both, always some of both. Sometimes it's 50-50. Sometimes you get more reflection, sometimes you get more transmission. When the media are similar, it's mostly transmission. When they're very different, we get mostly reflection. And if they're kind of similar, kind of different, it's about 50-50. Now, let's look at the part of the wave that is reflected, whether it's most of the wave or whether it's just a little bit of the wave. It doesn't matter. Some is always going to be reflected. That wave that's reflected may look real similar to the way that it went down, but it may look different than the way that it went down. Generally, we would say that the part of the wave that's reflected is reflected upright or right side up on the same side if the wave is going from high density to low density. In the demonstration we did, that would be the one where I was standing on top of the desk holding the slinky down. The wave was going from slinky to air, higher density to lower density. And you could see, I think fairly clearly, that it was reflected on the same side, or we would say right side up. It's reflected inverted, or it's reflected upside down. Now, let me put in brackets here. This is right side up. This is upside down. It's reflected inverted when the wave is going from medium that's less dense to more dense. That's when we had the little demonstration with Dammy holding onto the other end of it. It's going from slinky to person, and person is more dense than the slinky. The wave is reflected upside down, inverted. So we'll say that's low density. To high density. Now, what that often manifests itself as, low density, high density, whatever, that often manifests itself as a situation where the wave goes from high density to low density when the slinky or whatever it is not attached. The slinky was not attached to the air. The end was free to move. When Dammy was holding on to the end of the slinky was attached, right? So we're going from less dense to more dense. Whatever it is that's carrying the wave is usually attached. Going from more dense to less dense, whatever it is that's carrying the wave is not usually attached. So the first situation, it's me holding the slinky. It's just against the air. It's free to move wherever. Second situation is Dammy holding the other end of the slinky, where the other end was attached and was not free to move around. Now, we can't do this next part as a demonstration, but you're just going to have to trust me on this. It's called the law of reflection. If a wave strikes a boundary, it's going to reflect and transmit. But if it strikes a boundary at an angle, we're going to get something a little bit different going on here. Let's draw the boundary here. Here's the boundary. The wave strikes at an angle. We're going to draw a dotted line. That's going to be called a normal line. In physics, normal means 90 degrees. So that normal line is an imaginary line that's drawn at 90 degrees. The part of the wave that's reflected will be reflected such that theta 1 equals theta 2. The angle of incidence equals the angle of reflection. Now, the part that's reflected will be right side up or upside down, depending upon the boundary, depending upon whether we're going from more dense to less dense or less dense to more dense. Now, the part of the wave that's transmitted the part of the wave that's transmitted will change direction. It'll also change speed. It'll also change wavelength. What won't change? Part of the frequency. Once the wave has been made, the frequency will stay the same. So this wave, the green one that was going in here, part of it keeps going but changes direction. Part of it gets reflected, and the part that gets reflected such that the angle that it strikes it at is the same as the angle that it bounces off at. Okay, that's the law of reflection. The angle of incidence equals the angle of reflection. What we did above still holds, right side up, upside down, whatever, but the angles will be the same. That is of the reflected wave. Let's look at the part of the wave that keeps going now, the part that's transmitted. When we look at the part that's transmitted, there are two things that will always change, one thing that will sometimes change, and one thing that will never change once it's been made. What always changes? For the part of the wave that keeps going, that is. Not the reflected part, but the part that keeps going, that is transmitted. Yeah? The wavelength changes, yes. What else changes? Ben? Yeah. Hold on. The amplitude could change, but it would change depending upon how much of it kept going, right? If half keeps going, then the amplitude is going to be reduced, right? Because half of the energy was reflected, right? So absolutely, the amplitude can change, absolutely, because some will be reflected. It's not what I was looking for, but that's correct. The wavelength will change. What else will change? The speed will change. In fact, the wavelength changes because the speed changes. That's the most important one. The speed, then the wavelength changes as a result of that. What sometimes changes? Look at this yellow line right here. The green line comes in, and then the part that gets transmitted, the direction changed. We'll say theta changes. But that's only if it goes in at an angle like this. If it goes straight in, then its speed will change, its wavelength will change, but the direction is going to stay the same. So V changes always, lambda changes always, theta sometimes changes. What never changes? The frequency. Once the wave has been made, the frequency stays the same. Now you can choose to draw this next thing that I'm going to draw or not. It's just a little bit of an analogy to help you to understand why the speed of the wave changes, why the wavelength changes, why the direction will sometimes change, and why the frequency doesn't change. So again, choose to write it down if you want or not, whatever. There's a boundary between a parking lot that is paved and a swampy area over here. Maybe it's filled with a half a meter of water. Okay, you can walk in both. You can walk on the pavement, you can walk in the swampy water. Let's say for whatever reason we have a row of soldiers on this pavement. Here's one, here's another, and so on. There's my row of soldiers in this paved parking lot. If we're looking at these soldiers from above, let's say from a helicopter or a tall building, then it's going to look like one wavefront, like the crest of a wave looking at it from high up. Soldiers, we know, march in stride. They march together. They march at the same pace. So 30 seconds after this moment, this soldier is up here. Well, then this soldier is up here. And this one is 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 here. Like they're all marching together. This one, however, is walking in the swamp now. What happens to him or her? Slows down. So this soldier is now right there. Does that make sense? It's going slower because he or she is in a new medium, is in the swamp. Let's join the soldiers now to form the wavefront. Looks like this. Okay, 30 seconds later, this soldier is up here. They march together. Except this guy who's now in the swamp as well, who slows down. This guy's still in the swamp, so still going slower. Join them together, it looks like this. And one more, 30 seconds later. Now, this guy's in the swamp a little bit, This guy is definitely in the swamp. This guy's still in the swamp. This guy's still in the swamp. Join them together, and you get something that looks like this. Take a look at, first of all, the speed. What happened to the speed here? It slowed down. It changed, right? What else changed? The direction changed, right? The way the wave was going, the wave is going, the direction changed. What else changed? Look at the length of the wave here. Look at the length of the wave here. What else changed? The wavelength. What didn't change? Once the wave entered the new medium, once the wave entered the swamp, look at what we had. 1, 2, 3 waves per amount of time. What do we have over here? 1, 2, 3 waves per amount of time. What didn't change? The frequency, right? We still had 3 waves in the same amount of time. So, the part of the wave that gets transmitted, V, lambda, and theta change. The part of the wave that keeps going, or that, the part of the wave that gets transmitted, what doesn't change? The frequency doesn't change. Does that make sense? Yeah. Question?
They still walk the same way.
Yeah. Yeah.
Why we said
Question up here. Another good question was, aren't these soldiers still marching in the same direction? Yes, they are. But understand, this isn't really a wave, right? These are soldiers marching, right? This is an analogy, and this line that joins the soldiers together, it's not really a wave. It represents a wave for the analogy. So in the analogy, the line that represents the wave joins the soldiers together. The direction is changing. No, the soldiers aren't changing direction. Clearly, the direction of soldiers is staying the same. But in the analogy, what represents the wave is changing direction. Does that make sense? So you're right. You're absolutely right. But it's not a literal thing. It's just an analogy here. Okay?